On paper, a ship carrying 24,000 steel boxes, each the size of a small studio apartment, shouldn't be able to move efficiently. Yet modern engineering makes it possible, gliding steadily across the ocean. For every meter you increase the width of a ship to add more containers, you don't just add weight, you exponentially increase the wetted surface area. This creates a massive increase in frictional drag, requiring engines that consume hundreds of tons of fuel per day just to overcome the viscosity of water. This is the story of how we engineered a logistical miracle that is simultaneously a single point of failure for the global economy. This is the story of how we engineered a logistical miracle that is simultaneously a single point of failure for the global economy. Why do we do this? It comes down to a single metric: cost per TEU. If you move 5,000 containers on one ship, your fuel, crew, and port fees are distributed across those 5,000 units. If you move 24,000 on a single hull, those costs plummet. To put that in perspective, shipping a television from Shenzhen to London costs roughly the same as the price of a cup of coffee. But to achieve this, engineers had to solve the first principles problem of structural integrity. The ensing in the middle, the cost phenomenon causing. To prevent a 200,000-ton vessel from snapping like a toothpick, naval architects had to move away from standard carbon steel to high-tensile steel.
Steady on the descent!
As we scale up, we hit a wall, literally. The faster it goes, it creates a wave to the wave. Eventually, a ship becomes trapped by its own bow wave. To overcome speed limits without doubling fuel burn, engineers utilize the bulbous bow, increasing drag and fuel use. The bulbous bow smooths water flow, cutting resistance and saving up to 15% fuel. By creating a second wave crest that coincides with the trough of the primary wave, engineers reduce the wave-making resistance. However, there's a trade-off. This bulb is only optimized for a specific speed, usually around 18-20 knots. If the ship slows down to save fuel, slow steaming, the bulb actually increases drag. However, there's a trade-off. This bulb is only optimized for a specific speed, usually around 18-20 knots. If the ship slows down to save fuel, slow steaming, the bulb actually increases drag. Then there is the stacking problem. 20,000 containers isn't just a weight issue, it's a center of gravity issue. The center of gravity must be maintained to keep the ship stable and prevent it from listing. If containers are stacked too high, the ship becomes top-heavy, leading to a dangerous roll. To counter this, the heaviest containers must be placed at the very first out problem of the hold at the port. The ship is only half of the engineering loop. The other half is the civil infrastructure. A ULCV is useless if it takes 2 weeks to unload. Engineers solved this through automation and geospatial logistics. Modern ports use digital twins, software replicas the ship to calculate the exact sequence of every crane move. The constraint here isn't the crane, it's the load-bearing capacity of the dock. When a crane lifts 100 tons of steel, that pressure is concentrated on the rail tracks of the pier. Engineers must sink piles over 50 meters into the seabed to prevent the dock from collapsing under the weight of the logistics chain. So, is the 20,000+ TEU ship a triumph? The trade-off is systemic fragility. By putting all our eggs in one massive 400-meter-long basket, these ships are now so large they cannot fit through the original Panama Canal. They are limited to only a handful of deep-water ports globally. Technically, we can build bigger. There are designs for 30,000 TEU ships, but we have reached the economic point of diminishing returns. The cost of dredging harbors deeper and building larger cranes now outweighs the fuel savings of a larger hull. The cost of dredging harbors deeper and building larger cranes now outweighs the fuel savings of a larger hull. The 20,000 container ship is a masterclass in overcoming the physics of drag and the mechanics of stress, but it is also a reminder that in engineering, more is not always better. The 20,000 container ship is a masterclass in overcoming the physics of drag and the mechanics of stress. But it is also a reminder that in engineering, more is not always better. Human ingenuity can solve the problem of moving 200,000 tons across an ocean. The harder problem is building a world that can handle it when it arrives. Subscribe for more deep dives into the machines that build our world. To move 20,000 containers, you need more than just power, you need torque. These ships use massive, low-speed two-stroke engines that turn at only about 100 RPM. Why? Because of propeller efficiency.
A large propeller moving slowly is far more efficient at pushing a massive hull than a small one spinning quickly. But this creates a massive metallurgical challenge.
The crankshaft of these engines is a single piece of forged steel weighing over 300 tons. The sheer forces involved mean that the internal components are constantly under enough pressure to liquefy standard lubricants. For decades, the secret sauce of cheap shipping was bunker fuel, the thick, tar-like residue left over after gasoline and diesel are refined. It's cheap, energy-dense, and incredibly dirty. But we've hit a regulatory wall. The International Maritime Organization has slashed sulfur limits, forcing engineers to install scrubbers. Scrubbers clean the exhaust, ensuring compliance. These scrubbers use seawater to wash the exhaust, turning an air pollution problem into a water chemistry problem. It's a classic engineering compromise. We save the atmosphere by slightly altering the pH of the ocean in high-traffic shipping lanes. This is where the skeptical view comes in. Shipping companies are now marketing green methanol or ammonia-ready ships. Heavy fuel oil has a high energy density and is easy to store. Methanol stores less energy but is a liquid fuel. Liquid hydrogen has the lowest density and requires extreme cold. The physics is brutal. To have the same range as a traditional ULCV using green methanol, you would have to sacrifice nearly 2,000 container slots just for fuel storage. The truth about green shipping is that until the economics of carbon taxes outweigh the loss of cargo space, the 20,000 container behemoth will remain a fossil fuel giant. The final piece of the 20,000 container puzzle is data. Because these ships are operating so close to their physical limits, we can no longer rely on a captain's intuition alone. Modern ULCVs are covered in fiber optic strain gauges. If the hull twists more than a few millimeters, the bridge is alerted instantly. This isn't just for safety, it's for fuel optimization. By using to micro-adjust the heading based on wave frequency, engineers can save 1% in fuel. On a voyage from Shanghai to LA, that's $50,000 saved. Subscribe for more deep dives into the machines that build our world.